we were looking at the SGD, that is a stochastic gradient descent, and the batch technique to classify a specific pattern. And we observe that there will be difference, right, among the two techniques, obviously because SGD updates the weights instantaneously, right? For each and every data sample that you are trying to train the neural network, it calculates a delta term which is used to update the weights, right? And the weight gets updated at that moment as soon as a training data comes into picture, right? If you have capital N number of data training samples, the weight updation happens capital N number of times. That was the first concept we considered in the previous session. And after that, we looked at the second technique, that is a batch training technique, wherein you consider the batch. And batch, in the sense the complete data set can be considered as a batch. And for a batch, you calculate the updation in the weight, that is delta wi, you will definitely calculate. But for every training data, you don't update the weights, right? You wait until the complete data set, n number of samples, are completely used for training. Every time you calculate a delta w for each and every data sample, and you at the end, once all the n number of samples are used for training, you will calculate the what you call as average of the delta wi, right? So each value you got a delta w's and you calculate the average of those values, right? Once you get the average, then you update. So the fundamental concept here is like I update the weights only once, right, after the whole batch got trained, is used for training, right? Every time you calculate a delta w, keep it with you, keep incrementing the sum by that delta w value. At the end, you take the average by dividing by n, and you, right, try to do what is called as the weight update, right? We observe that, right, in terms of the time taken and in terms of the error, there is a difference. We observe that, correct? So in terms of the coding, you can see first we wrote the delta SGD. That was a code used to implement the SGD technique, right? For using the delta learning rule, for we used the SGD technique. Then we actually had tested that, right? So testing result yielded something like this. Then we also considered the delta batch, right, which was a code written, it's a function written to implement the batch rule implementation for delta learning rule. Then we tested that once again with the similar code, and that was a different answer, right? So we observed many things over here. Now our objective today is to compare the two techniques with another code. All right, so let's do the coding part. All right, so I want to have a comparison between the two techniques, namely SGD and the batch. Okay, let's try to do the coding for this. So we'll start with the input data. All right. I'll write the closing of all the unwanted windows and then clear the screen. Okay, now I will define my input vector, that is capital X is equal to, let's use the same data like we used yesterday. So 0, 0, 1. Then the second class was 0, 1, 1. Then another, that is 1, 0, 1. And the last was I think 1, 1, 1. All right. Okay, so we defined the data, right? This is the X. Then we'll define the target or the desired output values. Okay, so D is equal to, this is the 4 classes. So first 2 were belonging to 0 0, then the remaining 2 belong, it belongs to class 1 1. Okay, now let me assume that I'm going to make the epoch. Okay, how many epochs I want, I will define here. Epoch is equal to, let me define this to be, say, 1000. Okay, I'll define the number of epochs as 1000. Why I'm declaring this as a separate variable? Because I want to use this word epoch many times, right? If I use epoch only once, then the updation of this epoch number, if you want to change the epoch number, then you need to do this a lot of time, right? So I'll use a this thing called epoch. Okay, then I'll define 2 errors. Okay, so the first error, this is error for maybe SGD, right, is equal to, initially I don't have any error, so you can simply put zeros over there. Okay, this is zeros of, what should be the size should be that of epochs, because every epoch you are going to get an error. Okay, so this is the epoch comma, I'll just write 1 because I want only one column. All right, then I'll define another variable, that is error, and this time I'm going to check for the batch. Okay, that's also equal to the same as the error SGD. So initialize zeros, epoch, comma 1. Okay, so we define this now. Then let us try to define the define random weight vectors. Okay, so W for maybe I'll call W1, doesn't matter. So W for, this is for SGD, as I declared in the previous codes. I'll make it random. Okay, so maybe this is 3.5 times random of 1 comma 3, right, 3 inputs, that's why 1 comma 3. Subtract something from this, maybe I just want to minus, say, 2.8. You can make it completely random, doesn't matter. Okay, all right, so W1 is that. So now you see, I don't want to define W2 in another format, like another equation I don't want to write, because I want to initialize both with the same weights. So what I do, I call this is W2 is equal to W1, right? Whatever is W1 becomes the same weights for the second network as well, where I'm going to implement the batch method, right? Okay, so this is absolutely necessary, otherwise you get different weights for both the network. So when I declare both networks with the different weights, there is no meaning in comparing them, because one of them will have a closer weight to the optimum weights, the other one will have a weight value which is far away from the optimum values of weights, correct? So the point is that the one which is close to that will get trained quickly, right, will converge quickly. Other one is going to take a lot of time, there will be more errors. So there is no meaning in comparing both of them in that way, right, by defining different weights. So for that reason, it's clear now that why I am declaring both weights W1 and W2 are same. Okay, let's move further. Now let us try to okay, let's start with uh, the iterations. All right, so for, let me say, I is equal to, starting from 1 till the size of epoch. Okay, in the sense 1000 times do something. For I is equal to 1 till epoch. Okay, do something. What I am supposed to do, I have to calculate both the weights, once using SGD for first one, another time using the delta, the batch method. So we already have the two functions here. Let me just use the functions directly. Okay, so I'll simply pass W, I'll calculate. So that is W1 is equal to, call the first function, that is delta SGD. This was the function we wrote in the previous session. That is delta SGD of, pass the same variables, that is I have to pass the W1, pass the X and pass the D. Okay, this actually updates your weight W1, trains the machine using the SGD technique and the delta learning rule by applying the X and D for the weight W1. Similarly, I'll apply W2 now. So W2 is equal to delta SGD is over, use the delta batch technique and pass the similar this thing variables W2 comma X comma D. Okay, so it uses the previously written codes for this. Now we need to calculate the errors, right? So what we can do now, let us try to do okay, let's initialize two of the what you call error vectors. So I'll define the variables. I'll initiate the variables as zeros. Okay, let me call this is say ES1 is equal to 0, and I'll do ES2 is also equal to say 0. Okay, this is made 0, it's initialized as 0. Now I'm going to use these values. Okay, fine. So let's do the calculation over here. Okay, so here first let me define the n, the number of testing and training, number of data samples. Okay, I have 4 samples now. So, and I'll use another for loop for say j is equal to 1 till n. Okay, this is the second for loop, and I will declare the x is equal to capital X of this j, right? Every sample I need to read row wise. Okay, all jth row, read jth row all columns and take a transpose. Okay, that's my X, and I need to write the desired value. This is capital D of J. Okay, this is capital D of J. Now calculate the, I need to calculate the two outputs corresponding to both SGD technique as well as batch. So I'll call V1 my partial output. So V1 is equal to, you calculate as W1 into W1 should be multiplied with the input, that is X. All right, once you have V1 with you, calculate the final output, that is Y1. Y1 should be equal to how do you calculate sigmoid, right? So I think we have written a sigmoid function by the name my sigmoid. All right, I apply the V1 as input to that, so you get an output using this, and this is the error, right? I will calculate the error using what you call, I subtract desired minus the y value, and I'll square it. It's a squared mean square error. I'll show you the implementation of mean square error as well. Okay, so not a simple difference. Error, I think in the previous session we discussed about various types of error that we can calculate to compute the error term, right? The one of the technique is simple difference, like difference. So take a difference of target minus your output. That's a simple format of error. But today I want to show you a slightly different version of error, that is I'll take a squared error and then take a mean. Okay, mean squared error. I'll try to show you that technique now. So ES1 should be equal to the previous ES value, that means ES1 itself. Initially it is 0 plus now calculate the squared error. So the squared error is nothing but the desired value minus your current output. Okay, that is Y1. Right, this is a error, but I don't want error, I want a squared error, right? So if you remember, squared error is power 2. All right, I calculated the ES1 now. Very similar to this. This is this part of the code. The V1, Y1 and ES1 corresponds to which technique? It corresponds to the SGD technique. Right. Very similar to this technique. Now my intention is that I have to do the similar coding for the second technique, that is batch. Calculate the error. Then we'll try to plot both errors and visualize, right, how the errors are going to vary, right, when I change a technique from SGD to batch. All right, okay, so let's do the similar code now. So V2 should be equal to, it is W2, multiply that with the X. All right, then Y2 should be equal to my sigmoid of, say, this is V2, and calculate the ES2 is equal to ES2 plus the desired value minus the current output, that is denoted as Y2, and I want the squared error, right? So this is power 2. Okay, so both the what you call errors have been computed so far, right? So this has to be done for all the 4 values, correct? So once this is done, that is for j is equal to 1 to n, end this loop. Okay, the inner for loop we are trying to end. Once you finish and you get the error for the complete ES1 for one training, I can take an average, right? So I'll try to write it in this way. So this is okay, let's calculate. Therefore I think the errors, all right, let me define the error as maybe E of SGD of, I think this is I is the term which contains, if you run 1000 times, you get 1000 errors. So error SGD of I is equal to, right, the ES1 divided by capital N. Okay, similarly the error that is corresponding to, okay, already we defined that, sorry, my mistake. It has to be error SGD and error batch, my mistake. I already have used that. Okay, error SGD is already defined, you can see there, right? Similarly error batch is also defined. Okay, so this is error batch of I is equal to, this is ES2 divided by capital N. Okay, so you see we got the errors corresponding to, right, both the techniques. Then I end my the initial for loop, right, which was defined over here, right? So here now I got errors in the form of 2 different vectors, one for SGD technique, one for the other one. All right, so let us try to plot the 2 things, right? That is plot. Let me write this as the first function, that is error SGD, right? I can use a color for that. Let me ask it to plot it in the sorry, red color. Then I'll use hold on, because I want to plot something on the same this thing. Plot, right? That is the second one, error of the block, comma, right? Let me use say a different color and a different notation. So I'll use the black with this type of curve. Okay, then I use a legend. So what should be the first one? First one is SGD technique, and the second curve is the block. Okay, then right, anyway, you can use a title X label, Y label. Let's see whether this is going to work. All right, so the name in which I just want to save this is the SGD versus block. So just named this as a SGD versus block code. All right, let's try to run this. Let me say it says there is some error. Line number 17. Okay, this is 2.8. Okay, let me run this again. Error batch, sorry, I typed it, error batch 47. Right, now let's try to run this. Right, so we can see that a plot is generated, right? The red colored one is for the SGD, and the block shows block has been plotted as a dotted line, and it is in the blue color. Okay, so it is very clear that there is a difference in terms of the training process, and the error is also going to change, right, when you change your training method, right? So you can choose the technique that you want, right, and you can train the algorithm as per the requirement. All right, okay, so that's the one part. Whatever we had studied in the previous session, now we try to compare them, and that actually gave us a very clear idea that there is a difference. All right, there is a difference among what we are trying to implement, whether you go for a block, the batch method, or the SGD method. All right, okay, let's move further. Now the next topic that we are going to consider here is what are the various limitations of this kind of networks, which for example we are considering a single layered neural network, and there are the disadvantages or the limitations. Let's try to look at that now. Anyway, we have seen that once when we discussed the theory part, but let's try to recall that because that is very important. Okay, so the topic that we are going to look now is the limitations. So let's try to write this. Limitations of single layered ANN. Okay, now we actually have seen the problem of XOR gate, right? If you look at the scenario that we considered for an XOR gate, we understand that whenever the input data, right, input data is to be classified using a non-linear type of curve, right? So the classification should happen in terms of a non-linear curve, right? The single layered neural networks will fail. Okay, so let's try to consider a scenario now. So the input data that we are going to assume is like this. Okay, so let me consider one which is something like this. Okay, so look at my data set now. So I'll slightly modify my data in this way. So let me say that the data that I'm looking now is of the following type. Okay, so my data is, I'll modify my previously used data in the following fashion. So if I try to write 0010, where the last digit being the class Let me consider the 4 classes like this. Okay, so sorry, four data samples with the 2 classes. Okay, so that means this is one data and this is the other data. So 0 1 1 1, and I use the third data like this. This is 1 1 1 0, and let the fourth data be 1 0 1 1. Okay, let us try to use this as the inputs, and we can try to implement the delta SGD, right, for this particular data. And right, we will try to look at the output, what's going to happen now, right? So it's actually since this data set is in the 3-dimensional case, you may not be able to visualize that. This actually requires a nonlinear classifier, right? It looks very similar to the previous data itself, but actually if you try to plot and see along which axis you are trying to plot, you see the class 0 is along 0 0 1, that is just z-axis, and 1 1 1, that all the coordinates have values 1. Okay, x-axis 1, y also 1, z also 1, right? These two belongs to class 0, whereas 0 1 1 0 1 1 indicates nothing along x-axis, y and z 1 1, and x1 and z1, that is the last data, right? So this data is actually belongs to class number 1. So actually, right, it's something like our XOR problem, right? When we consider two inputs XOR gate and we try to implement using the simple neural network, we face the similar problem. Okay, that problem I'm going to show you now in terms of coding, right? Let's do the coding and let's try to implement the classifier for this specifically by using maybe okay, let's try to do this something like by using the code itself. Okay, let me try to implement this. Actually you can even look at the XOR problem over here. You can see first data contains 0 0 and the second data contains 1 1. So 0, when the inputs are 0 0 and 1 1, output should be 0. It should not classify, it should not be 0, right? And if the inputs are different like 0 1 and 1 0, output is 1, right? This is pretty much similar to the XOR problem itself. Okay, anyway, so let's go back to the MATLAB screen and let's try to implement this and check what's going to happen. Will the machine classify or not? Okay, I'll write a new code. All right, maybe I'll try to save it at the name, that is implementation of XOR gate using the delta learning rule. All right, so delta XOR. So it actually opens the new file with the same name. All right, now all right, so let us start writing the code from the first by first defining the vector x. So x should be equal to, first class is say 0 0 1, then the next one I want to give 1 1 1. Both belong to class 1, or you can even define with the variety. Okay, you can bring the first data belonging to class 0, next data belonging to class 1. So 0 0 1 1, this belongs to class number 1. Then I have 1 1 followed by this is the third dimension I keep as 1 always. All right, okay, that is 1 1 1 and 1 0 1. Okay, so this is how the x is defined. Now let's write the desired, that is capital D should be equal to, now the first one 0 0 means output should be 0, then it is 1. Whenever whenever the inputs are different, it should be 1. Then inputs are same in the third case, so 0, then it is 1. Okay, so this is the desired vector D, right? By default, I have to define a W now. So W is equal to 2 times random of 1 row, 3 columns, maybe minus 0.5. All right, define it like this way. Now let's go with the function that is called as I will use the what do you call, okay, we have to define the epochs, right? So for epoch is equal to how much? 1 to maybe 1000. Let's try with 1000 in the first case. Okay, so update the W is equal to let's use the first function. Irrespective of what we use, I don't think there will be any change. So this is the delta SGD of W comma X comma D. So once it gets updated, end. Right, then perform the testing with n equal to 4. Now for I is equal to 1 to 4, 1 to n, right? What I'm supposed to do, right? Define the x as the capital X of I, comma, all the columns, take a transpose, and I need to define the V, right? V is equal to the weight multiplied by this X. Okay, then calculates the you calculate the output, that is Y. We'll put it in an array. So Y of I is equal to the my sigmoid of say V. Okay, right. So pretty much similar code. It does this, and later on you simply display your Y value. Okay, so let's try to run this now. We have modified the values. Now you see, right? It has not learned anything. You can see that all the values are 0.5, 0.5, 0.5, 0.5. Okay, so let's look at the W itself initially. So W is equal to this. Let's see this so that we can make a comparison, right? Right, initial weight is that, and after learning I'll display the W once again. Okay, let's see this now. Right, there is updation, but the updation is not optimal. So you may say that you are not training enough, right? Let increase the what you call number of epochs. This is what we saw yesterday. If I increase the number of epochs, I'm expecting to that machine obtains its optimum weights, right? By training sufficiently large number of times. That means you increase the number of epochs, right? Let's do that and check now. So it was originally 1000, now I increased to 10,000. Okay, now let's see what's going to happen, right? I increased the training sample by 10 folds. It was 1000 increased to 10,000. I was expecting at least some improvement in the training part, but you can see it's 0.52, 0.5, 0.5, 0.52, right? Let's do another thing, right? That is, I will try to add another 0 and run. So you see, right? Even after training this so many times, right? I mean, now I increased by 100 times, right? Like I had 1000, 10,000, 1 lakh. Now the training happens 1 lakh epochs. But are you seeing any change in the weights and the updated weights and the Y values? No, they're not changing, because actually weight is not updating. Why the weight is not updating is because machine is not able to learn how to classify, because it knows to classify its capability is restricted to linear classification only, right? Since this data what we are giving is a non-linear data, it's not able to learn. Let's try increasing the number of epochs further, and we can go to any level and we can check this. Now you can see that it's training now, uh, but still no change, right? So even if you increase this by another by adding another 0, I don't think anything is going to change. Okay, it's training. Let's see what happens. So compared to the initial number, this is a huge number, so it's going to take some time for the training uh, purpose. Okay, uh, so right now we are implementing the XOR using a single layer neural network, and also we are using the SGD technique, right? Once this is going to run, I will show you what happens when we change this to, say, the batch technique. Okay, so anyway, so you can see the results on the screen, and it's very clear that nothing changed, right? Even after, right, increasing the number of training to 10 lakh and more than that, right? So it has not learned anything, right? It's still the final output it's going to give as 0 0.5, 0 0.5, 0 0.5, 0 0.5, right? Not the one which we are expecting, right? So let's check the same thing. Instead of delta SGD, let's change this part, only this part of the code. I'm going to call the batch technique. Okay. Let's try to run this. So you can see that this batch technique has not even learned what the SGD tried to learn. SGD at least changed something, but right, it is not changing. Let's increase and see will there be any change. No, no change. One more 0. Right? So obviously, right, let's do one more time, the last time. For the last time we added another 0, right? It looks like it's not going to learn, right? Obviously, right? Even if you add another 0 or 0 after that, 0 after that, it's not going to learn, right? Because it has it the problem which I asked this ANN to classify is out of its scopes, right? So it's not able to do that. So the point that we learned now is that we got actually two completely different sets. Training the neural network for a longer period does not make any difference. That's what we observed now. So the only difference, right, that we uh, understood here is that uh, the output variable, right, that y, right, is almost same for all the classes, right? That's what we observed, right? So instead of learning properly to identify the classes, it's not able to do that because of non-linearity in the final output classes. That means let's try to visualize the graph, what this problem was all about, right? Let's first look at that, then we'll analyze this further. Okay, so let's look at the data set, what we asked this machine to classify. So the data set which we provided for the machine, that is these 4 points. Okay, the 4 points are, right, you can see there the 4 points are like this. I'll paste once again, just a second. So the 4 data points which we considered, right, they belong to two completely different classes, and the classes are completely non-linear. So let's, right, so you can simply see that over here like this. So the zeros, the first two are x and y. So since z is 1 for all the four, we are not plotting the z axis, right? So just see the two classes. I'll just mark the two classes here. So this is class 0. This is also class 0. But where is class 0 over here? You can see this is a class 0. This is the class 0, correct? Whereas the class 1, right, if you see the class 1, that is this data and this data on our graph, right, they occupy like this, these two locations, right? So that means the data set which we try to implement, which we try to classify, right, has to be classified. It cannot be classified by simply using what you call the linear classifier or single layered neural networks, right? So what should be the ideal classification for this kind of data? It should be something like this. Just see now. So the one way of classifying them, this particular data using a nonlinear classifier should look like this, isn't it? So in order to have this, now you can see that this curve what we have drawn here is not a linear one. It's a non-linear one. It's some random shape, right? So in this kind of, if you have a data set which is like this, we will never be able to classify that using a single layered neural network. Okay, so our idea is that we have to implement something, right? If you want to solve these kind of problems, right, then we need to move on to the next type of the neural network. In theory, we have actually looked at that, right? So that is called as the multi-layered ANN. Right, so we right now our effort is to overcome the limitations of a single layered neural network. Okay, so the solution for that is nothing but a multi-layered neural network architecture, right? uh, Whenever we implemented the delta learning rule, right, and we understood that this is ineffective for training a multi-layered neural network because the delta can be calculated only for each of the stages, right? And the error you calculate in case of the delta rule, which is actually the essential for applying the delta rule for training, right, is basically not defined for the hidden layers. Because when I say multi-layered neural network, right, it has input layer, several hidden layers and an output layer, right? So the error that we calculate, right, it is applicable to which layer? It is applicable only for the final the output layer or the final layer. But how do you do the training associated with the hidden layers? There has to be some technique, correct? You have to find some technique to update the weights of hidden layer, because so far the delta learning rule updated only one layer, that is the final layer. There was only one layer, that itself was the final layer, obviously. But if you try to apply the delta learning rule to multi-layered neural network, it will update the weights of only final layer. Once again, you are dealing with only one layer in that case. So the fundamental thing with what we understand here is that this what you call delta learning rule is not enough, right? It is not capable of training the hidden layers of a multi-layered neural network. What's the reason? You understood now. Okay, and the error of the output node is simple difference between the correct output or the desired output and the current output of the neural network. So the training data does not provide correct outputs for the hidden layers, right? Means definitely the output layer will not classify, right? This is another view of the what you call the multi-layered neural network, right? Why you are using multiple hidden layers? Just to increase the learning rate. In the sense, whenever I give an input to my machine, right, the input layer, not the input, sorry, the hidden layers should be able to learn properly by updating their weights such a way that it gives some outputs to the output layer so that output layer can classify properly, right? But if you see there is no learning for hidden layers, then the output layer will never classify at all. So the main objective of introducing the hidden layers, right, will not get satisfied over there, right? So our idea should be, right, if at all the training data is not going to provide the required hidden layer updation, then definitely there is no classification, right? So that's a real problem now, right? So what we try to do now, right, the solution here is what is called as a back propagation algorithm, right? So error in the output is because of error in the hidden layer, correct? Obviously. So hidden layer is not doing the job, that's why the output layer is not doing the job. So make the hidden layer to learn properly, output layer will learn automatically, right? So the idea is that multi-layered artificial neural network, they use a slightly different algorithm, right? It is called as the back propagation. Right. So the significance of back propagation algorithm is that it provides a systematic method to determine the errors of hidden layers, right? So this technique systematically determines the error in hidden layers. This is required because unless the hidden layers learn properly, output layer will not learn, right? So once the hidden layer errors are identified, just add the delta rule at the end to adjust the weights. Okay, identify the error first, then you do the same delta is very efficient, we have seen that, but only thing was it was not capable to train the neural networks hidden layers. But if you know the errors of a hidden layer, then it is fine, because the error can be applied. If you know the error and you know the what is, if you know what is the expected output, that's the desired output D, definitely you can apply the delta, right? So then the delta can be applied. Okay, so then the delta rule can be used to update the weights. Okay, now let me show you the same concept by using the neural networks concept, right, with the help of a diagram. Okay, just consider this as our network. Now I am considering one hidden layer, right? So the hidden layer which you can see is at the center. So this is the hidden layer. Okay, so that is the hidden layer. Okay, Now, okay. So that's a hidden layer. Fine. And you can see that now, okay, I will mark the various layers as well so that it becomes easier for us to analyze what is happening. So this layer is which layer? This is the output layer. And let us say we have the input layer, which is collecting the inputs from various sources. So this is your input layer. Right. Now, normally we use the delta, right, rule to update the weights of this particular final layer, the output layer. Right. But now the concept is that since I have no idea about what is the desired output for each of the neurons that is present in the hidden layer, right, I may not be able to tell accurately what is the expected output of that layer. So for the current output of that layer, right, the hidden layer, I don't know what is the error, right. Once you don't know the error, you cannot apply the delta rule, very in a very rough sense. Okay, now I have to do an analysis like, okay, let's say the weights of a particular output, particular neuron in the output layer is say is fault, if there is an error. For example, so whatever they have highlighted with dark color, so there are some weights associated with this, right? So this and this. There are 4 weights which are wrong, right? The 4 weights are wrong means this particular value will be in error. That's why they have marked a EI. There is an error in that particular output. So that output is in error means these weights are not right. They are not correct. So from where you are getting these weights, they are coming from the outputs of, right, the hidden layer. So which actually means the inputs of those 4 hidden neural networks, right, are actually wrong. So you can see error is actually propagating backwards. So from the output layer, error is flowing backwards, right? So basically uh, the algorithm which takes care of this particular concept, that error is flowing backwards from the output towards the hidden layers. And if you have multiple hidden layers, through all the hidden layers, it the error is propagating back, right? So which error is propagating back in the sense training is not proper, weight updation of your hidden layers is also not proper, because of which your output is not proper, right? So this concept is called as the errors back propagation. In general, this is called as error back propagation, right? So we just look at the theory aspects of this. We have to look a little bit in detail so that we can understand the whole process in detail, right? So properly we can understand once we solve a problem first. Let's do some theory, right? We'll solve matrix representation kind of problems. We'll see the error is back propagating. We'll see the calculation of errors, right, for a simple network. Then we'll go for a code. We'll write a code and we'll do much more analysis of this particular technique. All right, so that will be done in the upcoming class.